In the last lecture, we completed PN junction diode with no applied bias. I explained barrier potential in the same lecture, and it is also called as built-in potential. Built-in potential. In case of no applied bias, we do not apply any external voltage source across these two terminals, and because of diffusion, we have depletion layer. Because of diffusion, we have depletion layer. Now, what is diffusion? Diffusion is the process in which free charge carriers or mobile charge carriers recombine with each other. For example, if we have immobile ion with hole, and if this hole combines with electron, then we have immobile ion with negative charge. On the other hand, if we have immobile ion with electron, and if this electron combines with hole, we have immobile ion with positive charge. Now, why this immobile ion is having negative charge on it, whereas this immobile ion is having positive charge on it? Because this hole is positively charged, and this immobile ion is losing one hole, so it will have one negative charge on it. On the other hand, electron is negatively charged, and this immobile ion is losing one electron, so it will have positive charge on it. And if you see the depletion layer, you will find on p side we have layer of negative immobile ions because hole combined with electrons, and on the n side we have layer of positively charged immobile ions because electrons combined with holes. So this is how we get the depletion layer, and it is called as depletion layer because it is depleted of free charge carriers. We do not have mobile charge carriers in this region, we only have fixed immobile ions. This whole process is also called as uncovering of immobile ions because when we have immobile ion and hole, the charge neutrality is maintained. When we have immobile ion and electron, then also charge neutrality is maintained. But when hole combines with electron or electron combines with hole, the uncovering of charge carriers takes place, and we have negatively charged immobile ion and positively charged immobile ion. And you can see the layer of negative immobile ions and layer of positive immobile ions act as the potential difference, and this potential difference is called as barrier potential. Now, why we are calling it barrier potential? Because it is acting as the barrier for the further movement of charge. This positive layer here will repel the holes, and this negative layer here will repel the electrons, and because of this there is no further movement of charge. Therefore, we call it barrier potential. It is also called as built-in potential, and in this lecture we will see the expression for built-in potential, and we will also solve one numerical problem on it. So if I draw the built-in potential or barrier potential, then initially it is 0. Then it increases like this, and the value is given by V subscript B. V subscript B is barrier potential, and we have to find out the expression for barrier potential V subscript B, and it is equal to KT by E natural log, in bracket we have Na Nd upon Ni square. So this is the expression for barrier potential, and the derivation is not important in this course. You only have to remember this formula. We will use this formula to find out barrier potential. This term KT by E is Vt. Vt is the thermal voltage. This is thermal voltage, or you can call it voltage equivalent of temperature, and Vt is equal to KT by E. We can easily calculate the value of Vt, and in numerical problems we will use the value of Vt directly. Now, what is K? K is Boltzmann constant. Boltzmann's constant, and it is equal to 1.1.38066 multiplied by 10 raised to power minus 23 joules per Kelvin. So this is the value of Boltzmann constant, and capital T here is absolute temperature, and it is in Kelvin. The unit for absolute temperature is Kelvin, and if you have temperature in degree Celsius, and you want to calculate the absolute temperature, then you can easily do it. So this is how you can find the absolute temperature. T dash is the temperature in degree Celsius, and you have to add 273 to it, and you will have your temperature in Kelvin. This is a very basic thing to know. For example, if temperature is 27 degrees Celsius, it means T prime or T dash is equal to 27 degrees Celsius. To find out absolute temperature, it means capital T, it is equal to 273 plus 27, and this will give us 300 Kelvin. So in this way you can find out absolute temperature. The next thing is small e. Small e is the charge of one electron, and it is equal to 1.6 into 10 raised to power minus 19 Coulomb. So we are done with the terms involved in the Volts equivalent of temperature or thermal voltage. Now we will see what we have inside this bracket. Na is the acceptor concentration, Nd is donor concentration, and Ni is intrinsic carrier density. So if we have all these things, we can easily calculate the value for Vb, that is the barrier potential. We will first calculate the value of Vt, the thermal voltage, because we will use it directly in numerical problems. It will save our time. So first we will calculate Vt. So let's do it quickly. Vt is equal to Kt by E, and let's say the temperature T dash, it means the temperature in degree Celsius is equal to 27 degrees Celsius. This is the room temperature. And as we are performing the calculations at room temperature, the value of Vt is also valid for room temperature only. K is equal to 1.38066 multiplied by 10 raised to power minus 23. Absolute temperature, capital T, is equal to 273 plus 27, and it is equal to 300 Kelvin. So we have 300 here, and the charge on one electron is 1.6 into 10 raised to power minus 19. And when you solve this, you will get 0.026 volts. So the value of Vt is 0.026, and we will use this directly in numerical problem. But there is one important thing: this value of Vt is valid for room temperature only. This is valid at room temperature only, because when you change the temperature, this number here will change, and the value of Vt will also change. But generally you will get questions in which the temperature is 27 degrees Celsius, or in question it will be given calculate the barrier potential at room temperature. In that case, we will take Vt equals to 0.026 volts. I will generalize this for any temperature T dash. We will generalize this. T is equal to 273 plus T dash, and this is in Kelvin. Vt is equal to Kt by E. T is equal to 273 plus T dash, so we have 273 plus T dash. I can write this as E by K. 273 plus T dash. E by K is 1.6 into 10 raised to power minus 19 divided by 1.38066 multiplied by 10 raised to power minus 23. And when you solve this, you will get 273 plus t dash divided by 11600. So this is the generalized form of Vt, and if it is not the room temperature, you can easily put the value of temperature here in degrees Celsius and you will have the value of Vt. So I will modify the expression, this expression, and Vb is equal to Vt natural log, in bracket we have Na Nd upon Ni square. So this is the formula we will use while solving the numerical problems. Let's move to the numerical problem. In this problem we have to consider a silicon p-n junction, at room temperature. Now we have room temperature, so we can say that value of Vt is equal to 0.026 volts, and it is doped at Na equals to 10 raised to power 16 per centimeter cube. Value of Na is equal to 10 raised to power 16 per centimeter cube, and value of Nd, the donor concentration, is equal to 10 raised to power 17 per centimeter cube, and intrinsic carrier density, it means Ni, is equal to 1.5. This is 1.5 into 10 raised to power 10 per centimeter cube. So Ni is equal to 1.5 into 10 raised to power 10 per centimeter cube. And we have to calculate the built-in potential. It means we have to calculate Vb. This is very easy problem. We only have to put the values in the formula. So we'll do it quickly. Vb is equal to Vt natural log, in bracket we have Na Nd by Ni square. Vt is equal to 0.026 natural log. Na is equal to 10 raised to power 16, so we have 10 raised to power 16 multiplied by 10 raised to power 17. Nd is equal to 10 raised to power 17. Ni is 1.5 into 10 raised to power 10, so we have 1.5 into 10 raised to power 10 whole square. 0.026 natural log 10 raised to power 16 multiplied by 10 raised to power 17 is 10 raised to power 33. 1.5 square is 2.25 into 10 raised to power 20, right? Or we can write it as 0.026 natural log 10 raised to power 13, 10 raised to power 33 divided by 10 raised to power 20 is equal to 10 raised to power 13, 2.25. 0.026. When you solve this, you will get 29.123. After multiplication we have 0.757 volts, and this is our answer. So the barrier potential or built-in potential is equal to 0.757, and this is for silicon p-n junction at room temperature. And in coming presentations also I will use barrier potential for silicon equal to 0.7 volts and barrier potential for germanium equals to 0.3 volts. This is very important because we will use this a lot. This is important, and this is calculated at room temperature. So this is all for this lecture. In the next lecture we will discuss width of depletion region. We will solve one numerical problem on width of depletion region. So this is all. See you in the next one.